Good morning, my lovely 12s. Right, buddies, today we are starting our very next lesson in integration. Title for today is Areas Under Curves, and this is actually a really important lesson for integration because finding an area under a curve, believe it or not, is one of the most important things that we will be doing in any of the sciences. So biology, chemistry, and physics all find areas under curves. And the reason why is because when you collect data in those subjects, you're able to put that data graphically, and oftentimes that'll make a curve instead of like a line like you're used to, and you'll want to find the area under that quite often just by considering the units. So, for example, say that you had like a graph in physics, and on its y-axis it had meters per second, so it had velocity or something on its y-axis, meters per second. Say that then on its x-axis it had time, so that might be measured in seconds. Well, if you were to find the area under that curve, so if you had like a curvy shape, kind of like this one here or something, and you were to try to find the area underneath that curvy shape, well, on the y-axis, the height that you'd be using would be in meters per second, and the width that you'd be using is in seconds. So when you times those two together, the seconds would cancel out. Meters per second times seconds would just be left with meters. So that alone tells you that when you multiply those two things together, when you find the area under a curve of meters per second and seconds, you're left with meters, which means velocity time graphs, underneath them, they produce a displacement or a distance because distance is measured in meters and that's what comes out. So yeah, it's really cool, and I think it's a neat topic, this area under curves. We won't go into it very deeply, but it is a really deep topic. But I'm just going to show you how to do it essentially today. Now, the proof for this is a bit complicated. It involves something called Riemann sums, which is certainly not something that we do at A level, but they're very cool anyway. But your textbook had a really kind of awesome way of just kind of doing a semi-proof of it, so I wanted to show it with you because show it to you. I don't know, because I thought it was neat and cool, so I'm going to show it to you. So how exciting! Okay, check out this graph here. Can you see that this little area here that they've got labeled in yellow is called A of x, okay? That's just to represent area. It's got an x in the bracket because it means area is a function of x. Now, see that weird little squiggly there in front of the A, the little squiggly guy there? It's actually the Greek letter delta. Now, you've seen delta before as like this triangle, so you've seen like change in y over change in x. That's actually a capital delta. The triangle one is a capital delta, and this little squiggly one is a lowercase one. They use the capital one for if there's big distances, like big differences in y and big differences in x, and they use this little squiggly one for if it's infinitesimal, which means that it's really tiny, the distances between them. Cool. This proof isn't important. Well, this proof is really cool, but you don't have to know it, so I'm going to try to erase it a little bit. Here's how it works, guys. See the little blue area that they've drawn right there? The proof works like this. If you consider this little blue area, which is supposed to be really thin compared to the whole area, if you break the whole area up into a whole bunch of little thin blue areas, and then you add up all the little thin blue areas together, that should equal up to the yellow area. Now, we know that that's not quite true because like the blue areas, if you draw them as trapeziums, they leave some extra space. And if you draw them as rectangles, they leave even worse of a space. You see what I mean? Like there's extra space there off the top if you were to do them like a rectangle. Now, here's how it actually works. What if you were to make that rectangle really thin? So consider this blue thing as actually a rectangle. If you made it really thin, you'd have less wasted space off the top. If you made it even thinner still, there'd be less still thinner area off the top. If you make it what we call infinitely thin or infinitesimally thin, then that means that there'd be zero space because actually the width of the rectangle would be zero, but it would still have a height. This is what this is showing you. See this little delta A? That means small a, little tiny area A, and again, you don't have to know this notation or even this proof, so if you're not interested, you can even skip if you like, but I still want to tell you. So yeah, this little delta A, that means this really small area of A should just be equal to Y, which is the height, like clearly, right? Y is how tall up it is. So yeah, it's the height times by how wide the strip is. So if this here, buddies, just to show you, if this is x, and this is x plus delta x, then that means the width here, that little section there, that's got width of delta x, right? Yeah. And this height, which is from there to there, well, that's got height y. because that's just the output value, right? Because if you were to track it over to here, that would have value y. So if you're going to do it as a rectangle, which is what we are going to do, because we're going to start shrinking our rectangles in a sec, then this should make sense to you. Delta A, the area, is going to be y, the height, times delta x, the width. Does that make sense, everybody? So it's not very surprising yet. Cool, cool, cool. But here's what happens. Oh, shoot. Oh, my God. Did I delete the page? Oh, my God. Okay, here we go. Going back, going back. Oh, yeah. Oh, thank God for that. Okay, which means then, guys, you can rewrite this equation. Delta A, then, the change in A, you can just divide by delta x. So delta A over delta x equals y. Cool beans, buddies? So instead of considering it as an area, you're saying the small change in A over small change of x equals to y. It's just dividing both sides by delta x. But buddies, check that out. What I want to have happen is I would actually like this wee area, this little red line I drew at the bottom, I want that to be 0, or as near to 0 as I can get it. Because the thinner I make my blue rectangle, the more accurate it is. If I make it infinitely thin, its width is essentially 0, which means its area would be essentially the height, which is really cool. Now we have a way of writing this in calculus, in differentiation and integration, and that's if you want something to go really, really tiny. We're actually talking about its derivative. Do you remember that from first principles, my lovelies? Yeah, do you remember when I told you that f prime of x was the limit as h went to 0 of f of x plus h, take f of x all over h? That's what we were doing there. We were shrinking the gap so much so that the gap was actually 0 at the end, and this is what you wind up with. So a wee change in a over a wee change in x, if you make it infinitely small, is actually the derivative of a with respect to x, because that means a super duper small change in both of those. Now, dA dx then, if this is what this is equal to, it actually equals y from this to there. Now, it doesn't approximately equal y anymore, because we've gone so close to infinitely small that it is 0, that just like this distance is 0. So we've even got equality. So we started off with like an approximation. We've actually achieved equality here, which means dA dx equals y, which is still useless because we're trying to find the area under a curve. But that means, buddy, oh shoot, oh, I just deleted the thing under the box instead of the box itself, which means then, badoosh, here's what you've got. A then, if you times both sides up, oh, I missed a step out, good heavens above. That means that you could rewrite this as this. You could write dA then is equal to y dx, if you split that up, integrate both sides, and you're going to be left with this. The integral of dA, it's like 1 dA, just equals a, and on this side it's the integral of y dx. And shaboosh, believe it or not, you have very, very, very much nearly proved with that the area is equal to the integral of the function with respect to x. OMG, guys, we just did a university level proof in like 30 seconds. Well, a nearly proof, I should say anyway. But isn't that really cool? So if you integrate the function, because that's what y represents as a function, with respect to x, you actually get the area under a curve. And that is the reason why. Now, I like to always tell you why, but at the same time, though, you don't need to know that. But what you do need to know is if ever you integrate a function, it gives you an area. Cool? It's not nearly so hard as that, though. Are you ready to have your minds blown with actually how not hard it is? As I picked the hardest possible question to show you, but still. Okay, here we go. This one says, find the area of the finite region. Do you guys know what finite means? I'll give you a hint, it's the opposite of infinite. That's right, it's a specific value. It means it's actually got a number. It's not infinite, it's got a number. It might be 6 or something. Of the region between the curve with this equation and the x-axis is what it says. Now, when we integrate, we always drop down to the x-axis, so the area that we're going to be finding will be to the x-axis. I'll show you in a sec. Cool. We're not really able to find the area of it right now because the first thing that we need in a hard question like this is a sketch. Okie doke. So we need a sketch of this monstrosity of 20 minus x squared. So let's do it, my buddies. Let's get it. So you can tell straight away it's got a minus x squared. It's a sad parabola. So it is like an upside down parabola. But to start with, we better get what the roots are, which means we got a factorizing job on our hands. So let's do it. Y equals minus x squared minus x plus 20. Just writing it from highest power to lowest. Cool. We got to factorize this bad boy. So times and pluses. Times is to make minus 20, adds to make minus 1. So the two numbers that pull that off, because I times the first by the last, is non-monic, don't forget. It's minus 5 and 4, isn't it? Those are the two numbers. So here we go, split the middle term, buddies, or however you like to do it is cool, because I know there's different methods. It's minus x squared, and then I'm going to put minus 5x plus 4x plus 20. Cool, so I split that middle term up, like we're used to from the start of the year. Cool, these two guys guaranteed to factorize, they have a minus x in common, so it's going to be y equals, pull that minus x out, that leaves you with x plus 5. These two guys as well, they're guaranteed to factorize also. So they have a 4. So plus a 4, brackets, x plus 5, which means our final answer here, y equals, and you're going to get the x plus 5 common, and you're also going to get a minus x plus 4, like a boss. Cool. Which means we can finally go to our final answer, which is going to be that x equals minus 5 if y were 0. So that's one of the roots. And then this similarly here, this is minus x equals minus 4, which means x equals 4. So there's our two roots. Give us a sketch so we can get the answer right. So here we go. Quick sketch, because our entire goal here is just to do the integrations. This is all bonus work at this stage. I mean, necessary, but bonus. Here's what you got. Crosses the axis at minus 5. Crosses again at 4. We don't need the y-intercept, but can you guys say what it is? Do you know what it is from our big pause, big neg table thing? That's it, it's 20. You got it. If x were equal to 0, it's going to cross the y-axis at 20. It's a sad parabola because the dominant term is minus x squared. So sad parabola looks like this. Oop, up through there. Lovely, lovely, lovely. Oh, I've got it more. I've got it popping on the wrong side. It looks like it should come down through the 20. There's more space on this side. So it comes up through. Do you know what? I think I've drawn it too sloppily, so I'm going to make it pop on the other side, even though I know it doesn't do that. There we go. Perfect. Just so it looks like a nice picture. I've not got it quite right. The peak should be on this left-hand side, but I've kind of put my minus 5 in the wrong spot. So it should pop there. But apart from that, all good in the hood. So, yeah, happy days. Okay, so that's what we got. Now, it wants to know, it says the question, it says it wants to know the region that's between minus 5 and 4, that's between the curve and that's between the curve and the x-axis. It wants us to find this area that's trapped there. Can you see that it's asking us that in the question? Do you guys follow that that's what it wants? Because it wants the equation between the curve and the x-axis. It wants this area here, okay? Okay, I'm going to label that area A, just to make it really clear for you that that's what I'm after, that area A. Cool. Now, just from a minute ago, when I told you a moment ago that the area is actually the integral of y dx, you don't really need to know too much about that. Here's what you got to know. You just got to know this. The area is going to be the integral of y. In this case, our y happens to be minus x squared plus minus x plus 20 dx. Can you see that the formula that probably none of the other sets have even heard of, a equals the integral of y dx, nobody even probably knows that formula because it's not necessary to know it, but can you see I just swapped out the y in that formula with this? Cool. That's the last time I'm ever going to talk about this formula. All you have to do, buddies, is integrate under the function. The function's minus x squared plus minus x plus 20. So integrate under that function and away we go. Oh, not quite yet. And we're going between minus 5 and 4. Use them on the bounds of the definite integral, I should say. So minus 5 to 4 is what we're going between. So let's do it. A equals, and open square bracket, as you know, minus is chilling, x cubed over 3, minus is chilling, x squared over 2, plus, and here's what we've got, 20x, okay? I don't need this plus c because I'm in a definite integral situation. Cool. So here we go. A equals, open circle bracket, put the number in, minus 4 cubed, put a bracket around it to be good, over 3 minus 4 squared over 2 plus 20 times 4. Oh, close first circle bracket, take away, open second circle bracket, minus 5 cubed over 3 minus 5 squared over 2 plus 20 minus 5, close bracket, right, and pop all that majestic stuff into your calculator. I'm so inclined just to look at the answers in the book and write that down, but you should type it in your calculator. I'll type it in too, and hopefully we'll get the same answer. Are you ready? Okay, negative, fraction button, 4 cubed, 4 cubed, oh shoot, negative, that's going to be 4 cubed, divided by 3, minus 4 squared over 2 plus 20 times 4, close bracket, close main bracket, take open bracket. This is going to be minus, then I'm going to put a bracket, minus 5 cubed divided by 3 minus 525 over 2. Yeah, that's it. Plus 20 times minus 5. Close bracket, close main bracket equals, I got 243. Oh shoot, I got 243 over 2, which is 121.5. So I think the area of this is 121.5. Now in questions like this, I know you want to put centimeter squared or whatever, but it doesn't actually tell us the unit. Say it was a question about physics, the unit might be like seconds or meters or something like that. So that's perfect. Hope you got the idea of that. Here's what I'm going to get you to do. Quick mix. So have a go at these. It doesn't have to be a quick mix actually. Spend, say, I don't know, 15 minutes on that because we're going to do one other topic today, but it's really related. So you can spend like 15 minutes on that. So you ready? Pause. Go. Okay, and you're back. Right then, guys. The final thing that we're going to do today is this. Areas above and below the x-axis. Now, sometimes, buddies, you're going to get functions that, well, pop above the axis and they pop below the axis. So sometimes there'll be portions of a function that's above and portions of the function that's below. Now, if that's the case, we still can find the area under it, but I'm going to tell you a bit of a secret here. I'll tell you a bit of a thing to this. Can you see this one, how the entire area was underneath the blue line but above the x-axis? That produces a positive area, which is what you saw, like it was 121.5. It was a positive area, so it gave a positive number out. Now, what happens is, if sometimes the function goes below the axis, that's going to give a negative area, which means that you're in a bit of a situation that if you get a negative area, it's not going to be ideal, because if you got some of it's negative and some of it's positive, they're going to cancel one another out, which means that if you get one that goes negative, you need to do each part separately, and that's pretty much it at the end of the day. Cool? So here's an example that shows us it, okay? So I skipped one of the examples and went right to this one. Okay. It says, sketch the curve with the equation y equals x minus 1x plus 3 and find the area of the finite region bounded by the curve and the x-axis. Cool, so that's just the area traced out. That's all that bounded means. Right, we got to draw it first, buddies. Okay, definitely we're going to want to draw it. Oh, and also it tells us to. So we can do my whole table method if you want, but I know that you guys are probably quite efficient at this now, so you might have outgrown my table, but I'll do the table just in case. So here we go. Sketch it out. Okay, sick. Here we go. Nice little axes for us here. Bang, bang. And in case, well, especially the one of you guys, I think it's 12A, I didn't actually teach this to, so yeah, you can see my method for the first time. Here's what you need to do to graph one of these. Roots, you need the y-intercept, you need big pause, and you need big neg. That's what you need, my buddies. If you know those things, you got a pretty decent idea of what the function looks like. Okay, so number one, my buddies, have a look. Here's our function here. And what have we got for our roots? In other words, if y was equal to 0, what would x be? Well, 0 with multiplicity 1, because there's no square or anything on it. It's just on its own. There's a 1, also multiplicity 1, and a minus 3. So those are our three roots. Hope you're happy with that. Coo. No squares, no cubes, no nothing. So there's none of that multiplicity stuff that we talked about earlier in the year. They're all just linear behavior as they cross the axes. Now, if y-intercepts when x was 0, so that'd be 0, that'd be minus 1, and that would be 3. If x were equal to 0, so 0 times minus 1 times 3, well, it's 0. Crosses it at 0. Okay, big pause. You need the dominant term for that. Dominant term comes from timesing x by x by x, which means the dominant term is x cubed. Cool. Put a huge number in x cubed, cube it. You get a huger number, plus infinity. Put a negative in. Well, it stays negative, but it gets huge. Negative infinity. Pop your dots on. 0, 1, -3. Like a boss. Okay, 0, 1, -3. 4, let's keep going in blue because I'm running out of colors. For the 1, this is in the big pause territory. So in the big pause territory, what we do is we cruise on up to infinity. In the big neg territory, which is below -3, that's the big neg territory down there, we're down to negative infinity, and you do a dot to dot in the middle. There's more of a gap between 0 and -3 than there is between 0 and 1, so it's going to be a tall bump here, popping down for a smaller bump there. Shaboosh, cubic legends. Now, here's the thing. I want the area, right? But there's two areas. There's this area here, A, and B. There's two areas. One's above the axis, A. One's below the axis, B. Now, spoilers alert, you can verify this on your own if you like, but if you think about A, it's going to be definitely a positive answer, but B, and you maybe should confirm this if you want, B is going to be negative. So say that this was, I don't know, 4 or 5, and this was 1. Well, it wouldn't be 1, it'd be -1, and that would give you a total area of 4. Well, that's wrong, though, because you don't take away areas when you're adding them together. You have to switch that -1 to a plus, and you go 5 plus 1 is 6, right? So to account for that, here's what you do. You do it in two parts. You go between -3 and 0 first, and then you go between 0 and 1 second. So you ready? Let's do it. Okay. Now, our function, it's a double tricky one, I forgot about that. It's a double tricky one because, to begin with, our function is y equals x. X minus 1, x plus 3. Yeah, that's not ready to go. That's not ready, is it, my lovelies? Because the only thing that we know how to do is powers, right? We only know how to do like power functions. This has brackets, so it's rubbish. So let's do it. Leave the x chilling. These two brackets together, they're going to be x squared plus 3x minus x. So that's going to be plus 2x. And then -1 is going to be -3, which means our final answer is x cubed plus 2x squared minus 3x. That's what we got. So there's our function in ready to go format. Cool. Integration time, buddies. So let's get A first. Get A. Right. So for A, guys, A is going to equal the integral, and we're going between -3 to 0. Yeah, not all the way, because don't forget, if I went all the way from -3 to 1, I'll get some negative areas in, which will cancel out, which is wrong. So it's the integral of this thing, the function, x cubed plus 2x squared minus 3x dx, because it doesn't make sense without the dx, and that's what we got. Integrate away. Let's do this thing. A equals, and square bracket now, add 1 to the power divided by the new power, plus 2 is chilling, 2x cubed over 3, minus 3 is chilling, x squared over 2, close square bracket, don't need the plus c, we're doing a definite integral, -3 and 0, sweet. Now, here we go, let's keep going, let's get our circle brackets in, A equals, the first one's easy, because putting 0 in just makes them all 0, 0 plus 0 take 0, take away, open second circle bracket, which should be taller than that. Oops. Open second circle bracket, and you're going to have this. You're going to have a -3 to the 4 over 4 plus 2 lots of -3 cubed over 3 minus 3. They're long a little bit, aren't they? -3 squared over 2, close bracket, A equals. Okay, so let's check it. I'm going to calculate it because I don't want to take any risks. Minus open bracket. E to the power of 4 is going to be divided by 4, though, divided by 4 plus 2 to the times 3 cubed, 2 minus 3 cubed over 3 minus 3 times -3 squared. And that's going to be divided by 2, close bracket. I got 91 over 4, or 22.75. I'm going to keep it 91 over 4, actually. Okay, so I got that, is this area. Cool. So that's neat. That's what this A is, okay? It's 91 over 4. That's what that is. 91 over 4. That's what that area equals up to. Okay, now same deal again on B, but actually we got a big shortcut to be had, okay? What's the big shortcut before I tell you what it is? Well, that's it, buddies. Well, if you look at it, the big shortcut is we're still integrating the same function, yeah? Which means it's got the same integral. All that's changed is that we're going between 0 and 1 this time. So essentially, I'm going to skip a step, and I'm going to steal a step right to here. I'm just going to change that beast over. B equals, it's going to be the same old stuff again, isn't it? Zoom in once here. It's going to be the same old thing again. So here you go, B equals, I'm going to zoom in one more time even. Okay, B equals, and here we go, it's going to be the same old thing. It's going to be x to the power 4 over 4 plus 2x cubed over 3. I'm not thinking, I'm just copying. Minus, oh shoot, I should have been thinking, I put the wrong number. Minus 3x squared over 2, 3x squared over 2. But the difference is, now we're between 0 and 1. So that's going to be between 0 and 1. Skip the step. How exciting. Okay, so here we go. B equals, and open circle bracket, it's going to be 1 to the 4 over 4 plus 2 lots of 1 cubed over 3 minus 3 lots of 1 squared over 2. Close circle bracket, take away, and thank goodness it's 0 again. 0 plus 0 takes 0. So that part you can just ignore. How exciting. Okay, B equals. And let's do it. So it's going to be a quarter, 1/4, plus 2/3 plus 3 minus 3 halves minus 3 halves, and by Jove, I got a negative number. It's minus 7/12. Take away 0. Oh dear. Now I just got a negative out, my buddies, which is not a problem, and it's to be expected because it's under the curve. Yeah, you get negatives when you go under the curve. I don't actually care that it's negative, okay? Sometimes I will. If this was a physics question or I was coming up with a formula or something like that, if I wasn't just simply finding area, I would be bothered that it's a negative. I'd care about that. This question's about finding areas. I don't care it's negative. A negative area doesn't make sense. It just means it's below the axis. So guess what I'm going to do? I'm going to switch it positive. It's 7/12. The area of B is 7/12, which means, my lovelies, go in for the kill. The total area then is just the two of them together. 91 over 4 plus 7 divided by 12 equals 70/3. And that is your final answer. Look at you, area finding legends. Say it was meters squared, it could be something like meters squared, centimeters squared. As I say, it could have been like meters if it was a graph of velocity versus time. It'd be meters per second if it was an acceleration versus time graph. It could be something different if it was like a graph of, oh gosh, I don't even know, like charge or something like that. You could get like Coulomb, like lots of physics things, okay, at the end of the day, lots of biology things, lots of chemistry things. All three sciences use these graphing transformation, or these graphing methods. Okay, integration is vital to all three. Cool. So that's it today. Have a little go at those. There's only 3 questions. Question 1's kind of like quite practicey. Question 2 and 3 are tricky, so I would make sure that you definitely try 2 and 3. But try a little couple of tricky ones from 1 as well. Like maybe try one, I don't know, like C, D, E or something if you're feeling good. And if you're not feeling good, try a like a 1A or a 1B just to make sure you get your head around it. Cool. So that's it from me then, lovelies. I know a bit of a longer video today, but I hope you have your head around it. I think next lesson I can give you practice even. So, yeah, we're flying. So good work, everybody. I'll certainly be seeing you next week. I hope I can see you this week, but I'm not all the way sure. And yeah, see you soon. Nothing to hand in this week. And I'll see you soon. Bye, lovelies.